Today we'd like to go a little farther with our study of parallel and series hookups for capacitors. So we saw that we can make banks of capacitors that can release amazing amounts of energy in a small amount of time. Let's today focus on the mathematics of figuring out what we can get from a combination of capacitors. Start with a simple setup of two capacitors hooked up in series with a battery. Remember that whatever negative charge comes out of the battery will be the same as the charge deposited on the negative plate of capacitor 1, and that will be the same as the charge on capacitor 2. So the first idea is that the charge is the same in all parts of our series hookup. We then want to figure out the total capacitance of our circuit. You do not just add them together. These act like resistors do in parallel. That is, every time you add another capacitor, you make it worse. You make less total capacitance. So, what we do is we add the inverses of the capacitors. So we would have 1 over the total is equal to 1 over 15 plus 1 over 42. Take a minute and pause it, and when you're done, see what you get. You should get a capacitance of 11 microfarads. Notice that we did not actually use e to the negative 6. As long as everything is in microfarads, we can work in whatever unit we want. All right, once we have our total capacitance, we now want to find our total charge. So we use the formula for charge for a capacitor, total capacitance times total voltage. We would use our total as 11, and we'd use our voltage as 6. This comes out to 66 microcoulombs. Okay, once we have the charge that came out of the battery, we can now find the voltage on each one of these capacitors independently. So we do Q1 equals C1 V1, Q2 equals C2 V2. Okay, so we use our 66 E negative 6. Capacitor 1 is 15 e to the negative 6. And we solve for voltage. We get 4.4 volts. Then we do the same thing for capacitor 2, 66 micro, 42 micro, and we solve for voltage there, and we get 1.6. We can see that our voltages add up to 6 volts, so everything is looking good. And finally, we can find our energy stored on the capacitor, 1/2 CV squared. And we plug in our total capacitance and our total voltage. Okay, and we get an answer of about 199 microjoules of energy. Not a lot of energy. These are not big capacitors, and they're hooked up in series. Remember, hooking them up in series makes us have less of a total capacitance. Okay, let's see how we do our parallel. So our parallel, take a minute and draw it out. We have two capacitors hooked up in parallel. We're going to have 24 volts on each because in parallel, all branches get the same voltage. We want to find the charge on each capacitor, so it's quite easy. You already have the voltages, you have the capacitances, so find your two charges. Remember, the charge that came out of the battery split. These are two separate charges. So to find the total, add them together. To find your total capacitance, you can add the capacitors together. To find your total energy, use your total capacitance, your total voltage, and solve for the energy. This time you should get a much higher number for both the charges and for your energies. Okay, so hopefully you guys can finish that. Work out all your details, solve for Q1, Q2, Q total. Then you can solve for total capacitance, and you can solve for the total energy stored on this system. So I hope this helps you work through your parallel and series connections for capacitors.